Welcome back to the virtual classroom of Chem-based School of Chemistry. Let's continue the discussion on the alkenes. In fact, in the previous lesson, we discussed about the various reactions of alkenes. I mentioned that alkenes undergo electrophilic addition reactions. We discussed the reason for it, the presence of the partially overlapping, the laterally overlapping the p orbitals, which has a great electron density. So the electrophiles are easily attracted by the weakly held pi bond. And then we discuss about the various addition reactions of alkenes, addition of hydrogen, which is hydrogenation reaction, addition of halogens to alkenes, which is halogenation reaction. And there are certain conditions for halogenation, such as the halogen should be in carbon tetrachloride, CCl4, to get the dihalo product. If not, the hydroxyhalo product will be produced. And then we discuss about the reaction with cold dilute acidified potassium permanganate to produce the diol. And then we studied about the reaction of preparation of alcohols by the reaction of steam to alkene. That's the lab preparation of alcohol. Then we discuss about the dehydration of the hexanol to form hexene. Right? Lab discussion on the various procedure carried out during the lab procedure. The reason for each and every step was discussed, and then the most important reaction was towards the end, that is based on the Markovnikov law, which is determined by the symmetry and asymmetry. When it comes to symmetrical alkenes, hydrogen halide, addition of hydrogen halide is not an issue to which carbon the hydrogen is and the halide is added. But when it comes to asymmetrical alkene, it is important to know the Markovnikov rule, that Markovnikov said that the hydrogen part of the hydrogen halide will attack the carbon, which already has a high number of hydrogen, to give the major product. I said the Markovnikov rule or Markovnikov law is helpful for us to predict the major product, but the Markovnikov rule or the Markovnikov law is not the explanation for the major product. It is not the explanation, but it is used as just for our convenience to identify the major product, but that is never the explanation. So the explanation, I said, is based on the mechanism and which is determined by the stability of the carbocation. We'll be discussing that today towards the end. So let's look into the mechanisms of heterolytic electrophilic addition reactions. Not all reactions, but we got only few mechanisms, not mechanisms of all the reactions. So the first mechanism is the addition of halogen to the alkenes, right? This mechanism is known as heterolytic electrophilic addition mechanism, right? Let's look into why this is called heterolytic electrophilic addition. So this is alkene. I'll just take propene. We know the halogens are added across the carbon-carbon double bond. I'm going to explain to you how two bromine atoms can be added across the carbon-carbon double bond to this molecule. Fine. So let's see how halogens can attack this molecule. Now, when it comes to halogens, we know halogens like chlorine or bromine, they are non-polar molecules. Chlorine, bromine, they are non-polar molecules. I'm going to explain to you how two bromine atoms can be added across the carbon-carbon double bond. So when the bromine molecule come close to this alkene, we know bromine is non-polar. So what happens is that this bromine molecule will get a temporary fluctuating dipole. That means two poles, a positive pole and a negative pole, but it's a temporary. A fluctuating meaning changing a dipole. We discuss about the temporary fluctuating dipoles under the intermolecular forces. That means when this bromine molecule come close to this alkene, alkene has a loosely held pi electron cloud. Alkene has a loosely held pi electron cloud, right? So what happens is that the loosely held pi electron cloud pushes the electrons of one bromine atom towards the other. That means usually bromine has electron cloud which is symmetrical, right? Because it is a non-polar molecule, so the electron cloud is symmetrical. So what happens is that when this bromine come close to the carbon-carbon double bond, the pi bond, the electron from one bromine atom will be pushed towards the other, right? Like this. If I'm to draw the other way, it's much better because it's already the pi bond. Imagine this is the pi bond. It's a loosely held electron cloud. So the electron will be pushed from one bromine atom towards the other bromine like this. Because of this pushing of electrons from one bromine to the other, there will be charge separation produced in this bromine, neutral bromine molecule. Even though the bromine molecule has no overall charge, it's a neutral molecule, there will be charge separation in the bromine molecule because of this pushing of electrons from one bromine atom towards the other. Now this happens because of the loosely held pi electron cloud, right? So then what happens is that when you have bromine, this is plus delta and minus delta bromine, the pi bond will be broken towards the plus delta bromine like this. But it doesn't matter which direction it breaks. It doesn't matter to which direction it is broken. So it can be on the left side or it can be broken towards the right side, right? So when this bond is broken, we know when a bond is broken, bond should be broken from the middle of the bond. The arrow should start from the middle of the bond and it should point in between the atoms where the bond is broken. So the bond starts from the middle and should be broken like this, right? And then the bromine, when this carbon on the left side forms a bond with the bromine cannot have two bonds. As a result, the bromine bond will be broken heterolytically. So this results in this molecule. There'll be bromine here, and a positive charge will be developed on the other carbon, bromine, and there'll be positive charge developed on the other carbon, right? So whereas the Br minus, which is produced as a result of this heterolytic fission, will attack this bromine, and that will result in the final product. Right? So what happens first is that the heterolytic fission of the bromine bond, because the bromine is a neutral molecule, but there will be a temporary fluctuating dipole like plus delta and minus delta, because whenever the bromine molecule approaches this pi bond is a loosely held electron cloud, and that pushes the electron from one bromine towards the other bromine, right? So that causes the bromine, which is a neutral molecule, to have two dipole, right? And then when this carbon, it doesn't matter to which direction it breaks, right? We'll discuss about the stability of the carbocation later on, and then you will know which carbocation is most stable to be found first, but it doesn't matter in this mechanism, whatever direction it breaks at this stage. And then you get this carbocation here, as this pi bond is broken towards this bromine. You get this carbocation, and then you get the Br minus, which is formed as a result of the heterolytic fission of the bromine bond attacking this carbocation. Now the thing is, whenever a bond is broken, the arrow should start from the middle of the bond and it should point in between the two atoms where the bond is formed, right? Middle of the bond is should be started, and it should be a fully headed arrow because we know electron pair is moved. So you should not use fish hook arrows here. Electron pair is moved, so fully headed arrow in between the two atoms, and then the bromine bond should be broken heterolytically. Then again, it should start from the middle of the bond and should point to the atom where the bond is broken. When a bond is formed, the arrow should start from the negatively charged species here, electron rich to electron poor always. The arrow will move from electron rich to electron poor. So it will start from the Br minus and should point in between the bromine and the carbon like this, right? So why do we call this as heterolytic electrophilic addition mechanism? You know, the heterolytic fission takes place here, right? You can see the carbon-carbon bond fission is a heterolytic bond fission, and the bromine-bromine bond fission is also heterolytic bond fission. So that's why we call this as heterolytic, not homolytic. Earlier, free radical substitution was a homolytic bond fission, right? Here it's a heterolytic. All the bonds are broken heterolytically. That's number one. And then it says electrophilic. Why this is called electrophilic? Because the electrophile attacks first, right? Always a mechanism is named after what species attacks that molecule first. You can see the Br plus, which is electrophile. What is the electrophile? Electron lacking species, which itself is electron deficient. You can see the bromine is electron deficient, right? So that is what attacks this molecule first. Always when an electrophile is attacked, it is followed by a nucleophile. See, second attack is a nucleophile, nucleus loving species, but the mechanism is never named after the second attack. Now, any mechanism is labeled, named after the first attack, right? What attacks the molecule first? So always when an electrophile is attacked, a nucleophile will follow. A nucleophile is attacked, electrophile will follow. But the mechanism of a reaction is based on the first attack, right? So this is heterolytic electrophilic addition. Why addition? Because bromine atoms are added to the molecule. The most important thing is now see this bromine molecule is acting as an electrophile, right? But it is overall a neutral molecule. This is a good example to show how a neutral molecule can be an electrophile. How a neutral molecule can be an electrophile, right? Because electrophile is not necessarily always it has to be a positively charged species. Electrophile possible to have be positive, but electrophiles are never negative because negatively charged species will never lack electron. Rich molecule because alkenes are electron rich because of the pi bond, right? So electrophile can never be negative. Electrophile can be positive or it can be neutral, and this is a good example for a neutral electrophile. So overall, even though bromine has a delta positive charge, the overall molecule is neutral. Yeah. So halogens, bromine and chlorine undergo heterolytic electrophilic addition reaction with alkene. When halogen is added to when halogen is added, it will polarize as plus delta and minus delta when come closer to the pi electron cloud as a bond is relatively weak. Therefore, the bond will be easily broken as a pi electron of alkene approaches the molecule of halogen. The plus delta halogen accepts the electron and releases a shared electron to the other halogen atom. Therefore, the electrophile X minus, the halide ion, adds to the alkene, followed by the X minus, which attacks the carbocation. Right? This is X plus delta should be this is plus delta, adds to the alkene, followed by X minus, the halide, which attacks the carbocation. You have to know all these steps as I have written, right? Only thing is your alkene will differ. You don't get propene always. It can be ethene, propene, butene, any alkene. But when you draw the mechanism, you have to highlight the carbon-carbon double bond part of the molecule. It doesn't matter what these groups are. Doesn't matter what those groups are. So you simply highlight the carbon-carbon double bond, what I have done. Right? So you'll get to draw the entire mechanism. When you tell to draw the mechanism in the question, you have to draw the molecule and you have to show all the arrows, how the arrows move, all the charge. You get at least 3 marks for this. 1 mark goes for the correct movement of the arrows from where it begins, where it ends, where it begins, where it ends matters, and 1 mark for all the charges, plus delta, minus, plus, all these charges properly written, another mark. And the third mark is for the structure of the carbocation, which is formed as an intermediate. Right, you have to get, you don't need to get to draw, need to know to draw all these steps, right? The initial, the intermediate, and the final. All the arrows with all the partial and full charges and the movement of the electrons. Clear? You can copy this. If you have any questions, let me know. Right, the next is the mechanism for the reaction of hydrogen halide to symmetrical alkenes. Right, so we'll take a symmetrical alkene, which is ethene, or I can take butene. Hydrogen halide is already a polar molecule. It has permanent dipoles, plus because hydrogen halide is there's a difference in electronegativity between the halogens, so it has a permanent dipole, right? It has a permanent dipole. So what happens is that, like I explained before, this is a straightforward mechanism. Since the question says bromine, let me write Br here, right? So this hydrogen halide is already polar. So the hydrogen part is what attacks this carbon-carbon double bond. The bond breaks, and then it doesn't matter to which direction the bond is broken. You can break the bond this way, or you can break the bond the other way. If it breaks the other way, then this carbon gets the hydrogen, right? So then what happens is that this carbon gets the hydrogen over here. That's the left side carbon, and then the right side carbon gets a positive charge, where the Br minus, which is produced as a result of this heterolytic fission, attacks this, resulting the product. Right? So it is almost similar mechanism like what we discussed before, the addition of bromine. So this is quite straightforward, unlike this where the temporary fluctuating dipole is produced when the neutral bromine molecule approaches the pi bond, but here the hydrogen halide is already polar, right? So the correct orientation is important here, which means if bromine meets the double bond first, the reaction will not take place because bromine is negative, right? So the reaction will not take place if the bromine meets a double bond. So hydrogen has to face a double bond first because it is delta positive. So the electrophile, the H plus attacks his molecule first, right? That's how it is electrophilic. Again, this is heterolytic, electrophilic hydrogen mechanism, right? Because the H plus is the species which attacks the molecule first, and then the hydrogen halide bond is broken heterolytically. Then once the carbocation is formed, the halide ion attacks the carbocation, and it doesn't matter to which direction the bond is broken because it is a symmetrical molecule, right? So alkenes undergo heterolytic electrophilic addition reaction with the halogen or hydrogen halide. The electrophile hydrogen bromide, the electrophile HBr is a polar molecule,